Okay. Ah, ah,
All right, welcome to week 8. As usual, I'll give you hints to solve the assignment questions. Let me open the questions first. Question 1, straight true or false. Transmit diversity scheme allows. array gain. Since it's a true or false question, you can refer to lecture 36. Second question, what is the net degree of freedom for the Alamoti scheme for two transmit antennas? You can go back to your lecture videos and see what the Alamoti scheme is. And you have two transmit antennas. We will show that equivalently you transmit two symbols over the two channel users. Well, degree of freedom. Let me just say the net degree of freedom will be number of symbols the channel use. Now for this scheme we should be able to figure out what is the number of symbols per channel use. A receiver has two antennas and performs maximal ratio combining to improve the bit error ratio. Both the receivers are uncorrelated and follow Rayleigh distribution. One of the antennas has an average SNR of 5 dB. I just change the numbers. And the other has an average SNR of 10 dB. What is the average SNR after maximum ratio combining? So maximum ratio combining you'll have gamma MRC is gamma 1 plus gamma 2. So the average, the expected value is the expected value of gamma 1 plus gamma 2. But if you know a little bit of probability, you know that expected value is expected value of a sum is the sum of the expected value. So it's the expected value of gamma 1 plus expected value of gamma 2. Oh, that is what they have given. Expected value of gamma 1 is the average SNR. Here gamma 1, gamma 2 are the SNRs. So the average SNR are 5 and 10. But so here we are adding, so you have to be a bit careful. So this is, you have to write in linear scale. 10 power 0.5. And the expected value of gamma 2 is 10 dB, which is in linear scale 10 power 1, just 10. Which will turn out to be 3.16 plus 10, 13.16. And if you want the answer to be in dB, you have to take log to the base 10 of that. And then multiply by 10. It will be 11.2 dB. So you have to be careful. You shouldn't add the quantities in dB directly. I just taken some example numbers. In your assignment, you will have different numbers, but the formula will be the same for maximum ratio combination with two uncorrelated antennas. Given that the DBPSK modulation scheme is being used, find the BR performance of the above system. Okay. Okay. For DBPSK, the bit error probability P error DBPSK fading. This is given by half of psi of gamma MRC of S evaluated at S is equal to -1. This I think there is a derivation in lecture 35 or something. Okay, you should go and check in lecture 35. And this will turn out to be n s is -1. So there are two receivers, so there are two terms. And the terms are of the form 1 minus s gamma, and gamma is the SNR. So s is equal to -1, so the terms will be here 1 plus gamma simply. So the first term is 1 plus, in our case, gamma was for the receiver 1 pi dB, right? Average SNR. Pi dB, again you have to write in linear scale. It's 10 power 0.5 into 1 plus the gamma for the second receiver, which was 10 power, which is 10 dB, so it's 10 power 1. This is half into 1 over 4.16 into 11. This will be 0.011. Again, in your assignment, you will have different numerical values, but the method of solving it is the same. Formula is the same. Question number 5. In the above question, the branch with 8 dB SNR has Nakagami M fading instead of relay fading with M is equal to 2. Find the new BER. Okay, in this new scenario, we are still following the BPSK. I'll just write it as fading. So now it's half. First receiver, there is no change. It's still Rayleigh fading. So the term corresponding to that is still 1 plus S gamma. 1 minus S gamma. S is minus 1. Gamma is 5 dB. So it's still 1 plus 10 power 0.5. The change happens in the second term, which is Nakagami N fading. The change is, so it's 1 plus gamma divided by 2 whole square, since M is equal to 2. So it gets multiplied by a factor of M, and the SNR gets divided by a factor of M. This will be again 1 over. First term is same 4.16. Second term is 86. So here you can see that the second term is larger. So the beta probability is actually smaller when you do MRC. This is 0.0033, much smaller. Again, for derivations of these formulas, you'll have to go and see the lecture. And if you have a doubt in the derivation, then you can ask a question in the Q&A group. I'll clear that doubt next week. Question 6 is, will there be any difference in average SNRs with conditions given in question 3 and question 5? So question 3 and question 5 have the same kind of scenario. There are two receiving antennas, and the average SNR of one antenna is 5 dB average SNR. at the other antenna is 10 dB. Only thing different between question 3 and question 5 is that in 3, for both the receivers, we are using relay distribution, but in 5, for the second receiver, we are assuming Nakagami M distribution. So will that change the average SNRs? Can't directly tell you the answer, but I can give you. Note that the average SNR, capital gamma, after doing MRC, V of gamma 1 plus gamma 2, V of gamma 1 plus E of gamma 2. It depends on the average SNR of the antennas. In question 3 and question 5, is the average SNR changing because the distribution is changing, or is it not changing? So here you see in the formula that there's no dependency on the distribution. There is only dependency on the average SNR. Of course, will the average SNR change with the change in the distribution? That you have to decide yourself. Question 7. In question 1, instead of using MRC, we had done EGC. Find the average SNR after combining. So in question 1, I think there is a typo here. Question 1 was a true and false question, which has nothing to do with this. I think they meant question 3. So this is actually in question 3. So question 3 was the receiver has two antennas and performs maximal ratio combined. Both the receivers are uncorrelated and follow relay distribution. One of the antennas has an average SNR of 5 dB and the other has an average SNR of 10 dB. What is the average SNR after maximal ratio combining? I think they mean in this question, instead of maximum ratio combining, we do EGC. What is the average SNR? Suppose there are M antennas or M receivers, then the average SNR, if you do equal gain combining, is 1 over M summation of the square root of the average SNRs, the whole thing squared. So here M is equal to 2. And gamma 1 is 5 dB, gamma 2 is 10 dB. So try to find out the average SNR. Okay, here this is uh, not the average, this is the instantaneous value. So average SNR is the expected value of that. So try this yourself. In the meantime, I'll go to the washroom and come back. But I've given you the formula, and also you have to remember that the the antennas are uncorrelated. So E of xy for two uncorrelated random variables x and y, E of xy is E of x times E of y. I can use that here. Try to solve it yourself. I'll be back in a few minutes. Okay, so here M is 2, gamma EGC is half of square root of gamma 1 plus square root of gamma 2 whole square, which is nothing but gamma 1 plus gamma 2 plus 2 times square root of gamma 1 times gamma 2. Now we have to take the expected value of that. When we take the expected value, this will become half of expected value of gamma 1 plus gamma 2 plus 2 root gamma 1 gamma 2, which is half of E of gamma 1 plus E of gamma 2 plus 2 E of, but the antennas are uncorrelated. We can write this as now gamma 1 has average value E of gamma 1, that is what is given for us. Square root of gamma 1 will have that. I leave it as an exercise for you to verify. That square root of gamma 1 has mean square root of pi gamma 1 over 2. Now this will become half into 10 power 0.5 plus 10 power 1 plus 2 times 5 over 4 into square root of 10 power 0.5 into 10 power 1. Yes, be approximately 11 in dB. It will be 10.4. Of course, you have to remember that I've taken different numerical values than your assignment question. So you really have to do the calculations yourself. Don't just see the solution and go and try to find the answers. There's no 10.4 dB in any of the options. Question 8, BR depends on which of the following modulation scheme, type of fading, antenna diversity. So we saw BR for two different fading cases. Of course, this was for after doing MRC, but still saw that when we had Nakagami M, we had a different BR when compared to Rayleigh. That will hold true even in the general case. So type of fading does affect the bit of the rate. Other two things, antenna diversity and modulation scheme, you have to go and see in the lectures. Whether modulation scheme changes BER. Of course, you can make a guess just by seeing the formula for BER. We are writing dBPSK. If it didn't matter if it was same for all modulation schemes, then we wouldn't really specify its dBPSK here, right? You can make a guess, but to understand why BR depends on modulation scheme, you have to see the lecture. Next question is also just a multiple choice, theoretical, conceptual question. Which of the following statements is not correct? Array gain is absent in a non-fading environment. Array gain causes a shift in the BR curve. Diversity gain improves the statistics of the SNR in a way that reduces the BR. All of the above. So we have seen in several problems last time and in lecture notes everywhere, the diversity gain does change the SNR so that BR is reduced. So that rules out option C and D. Then I leave it to you to check A and B and figure out which of them is not correct. Question 10 for the Alamoti scheme discussed in the lecture. The diversity order was found out to be to consider a modified Alamoti scheme, where two receiver antennas are present. One can write down the matrix equations for the second receiver antenna similar to the case in which only one receiver antenna is present and combine the matrix equations for the two receiver antennas to get a single matrix equation for the entire system. What will be the diversity order for this new system? Okay, the setup is like this: two transmit and two receive antennas. and what you transmit are S1 and S2. That's what antenna 1 transmits, and antenna 2 transmits minus S2 conjugate and S1 conjugate. So we are simply copying from the Alamotti scheme. Okay, there you had only one receive antenna, and the gains were just Z11 and Z21. Here you have two receive antennas. That's the only difference. Let RIN be the received symbol at antenna I at time n. Then R1 times 0 is at time 0, antenna 1 is sending S1 and antenna 2 is sending minus S2 conjugate. And from antenna 1, transmit antenna 1 to receive antenna 1, the gain is Z11. From antenna 2 to antenna, transmit antenna 2 to receive antenna 1, it's Z12. So at time instant 0 is what is being sent. What is being received at the first antenna is Z11 times whatever the first antenna is sending, which is S1, plus Z12 times whatever the second antenna is transmitting, which is minus S2 conjugate, plus noise. Similarly, R2 0 is Z21 S1 plus Z22 minus S2 conjugate plus noise. Then at time instant 1, when TX1 is sending S2 and TX2 is sending S1 conjugate, R11 is Z11 S2 plus Z12 S1 conjugate plus N11. R21 is Z21 S2 plus Z22 S1 conjugate plus n21. If you write it as a vector, r10, r1 conjugate 1, r2 0, this you can write in matrix form as so r11 conjugate is the conjugate of this, which is z12 z12 conjugate s1. So it's z12 conjugate s1, and then z11 conjugate s2 conjugate. R20 is z21 s1 plus z22 into minus s2 conjugate. So it's minus z22 into s2 conjugate. And R21 conjugate is z21 conjugate s2 conjugate. So it's z21 conjugate plus z22 conjugate s1, and the noise is n10. Second one we wrote the conjugate form, n11 conjugate, n20 to conjugate. So this is your Z matrix. This is S symbol vector, zero noise vector, and receive vector. So you can write R is ZS plus N. From this you can find Z Hermitian Z as Z11 conjugate Z12, Z21 conjugate Z22, minus Z12 conjugate Z11 minus Z22 conjugate Z21 times Z11 minus Z12 Z12 conjugate Z11 conjugate Z21 minus Z22 Z22 conjugate Z21 conjugate, which is the first row times the first column will be Z11 conjugate Z11, which is mod Z1 whole square plus Z12 times Z12 conjugate, which is mod Z12 whole square. Similarly, other terms are also mod Z21 whole square plus mod Z22 whole square. The first row times the second column is Z11 conjugate minus Z12 plus Z12 times Z11 conjugate. So that is 0 plus Z21 conjugate minus Z22 plus Z22 Z21 conjugate. That is also 0. Is 0. Similarly, this term will also be 0. And this term will again be mod Z12 mod Z11 whole square plus. Now, since R is Zs plus N, Z Hermitian R is Z Hermitian Zs plus Z Hermitian N, which is summation I is 1 to 2, j goes from 1 to 2, mod Zij whole square plus this you can write Z Hermitian N, you can write as W1, W2. Z Hermitian is a 2 by 4 matrix and N is a 4 by 1 uh, vector, so you'll get a 2 by 1 vector. Okay, up to this I have done. From this point, I leave it to you to find the output and the diversity order. So you simply have to go back to the lecture and see what we are done for the case of single receiver antenna. A small portion is left after this. So that small part you have to do. If I do it, then that'll directly give you the answer. I'll leave that remaining part to you. We'll go to question 11. Consider a channel with SNR 20 dB. What is the capacity? Let me do it with a different number at least. Take SNR as 10 dB. What is the capacity of the channel per unit bandwidth? We're talking about AWGN channel, okay? And in that case, the capacity or bandwidth, let me just say capacity is bandwidth times log to the base 2 of 1 plus SNR. So capacity per unit bandwidth is log to the base 2 of 1 plus SNR. In this question, the SNR is 10 dB, so it's 1 plus 10, which is 3.46 bits per second per hertz. Okay, I'm sure you can change the numbers and solve your assignment question. And for a Nyquist pulse shaped signal with unit average signal power, the capacity of the channel depends on options are the modulation scheme, receiver sensitivity, symbol rate, all of the above. The capacity is B times log to the base 2 of 1 plus SNR, which is B times log to the base 2 of 1 plus PS by Pn. Noise power is 1 plus PS by N0 B. Now, unit average. The given average signal power is 1 unit average signal power. Yes. So capacity depends on what quantity now. Bandwidth. And what does the bandwidth depend on? In Nyquist, for a Nyquist pulse shape signal. So P depends on B for Nyquist pulse shape signal. What does B depend on? So does it depend on modulation scheme, receiver sensitivity, symbol rate, or all of the above? That I think you can answer yourself. Consider a channel with free space path loss. What is the normalized capacity of the channel when the transmitter and receiver are separated by a distance of 150 meters. Assume that transmit power is 30 dBm, receiver noise minus 80 dB watts, carrier frequency 900 megahertz. The receive SNR is the transmit power minus path loss minus receive noise power. It is given that path loss is free space. We have to go back all the way to lecture, the first week of the lecture videos, and remember what is free space path loss. Given that the transmitter and receiver are separated by 150 meters, the path loss will be inversely proportional to square distance. So to find the path loss, transmit and receive power are already given as 30 dBm, and transmit and receive noise is already 30 dBm and minus 80 dB watts. Then you can simply find the capacity per unit bandwidth is log of 1 plus SNR. 14 to 18, consider a fading channel with instantaneous SNR given by gamma is alpha square capital gamma, where capital gamma is 20 dB and alpha is the instantaneous fading coefficient that varies with time. Bandwidth is 20 kilohertz. The probability distribution of alpha is as follows. Alpha and P alpha of alpha are given. I won't write down the values. Question 14 is what is the average SNR of the channel? Oh, instantaneous SNR is gamma. Average SNR is expected value of gamma. Now gamma has only four possible values with non-zero probability. In this case, the expected value is the uh, SNR gamma I times the probability of occurrence of that SNR P alpha of alpha I, where I goes from 1 to 4. But gamma is alpha square times capital gamma. So this is alpha I squared P alpha of alpha I times capital gamma. So you know the value of alpha I and P alpha of alpha I. Four different values are there. From that you can find this quantity. And you already know gamma is 20 dB. So now you just have to plug in the values and find average SNR. Then can you find an upper bound on the channel capacity using Jensen's inequality? So using Jensen's inequality, let me see. The upper bound will be B times log of 1 plus average SNR, where we found the of gamma in the question number 14. Then question 16, what is the ergodic capacity of the channel? Ergodic capacity is the average expected value of the capacity, which is the sum of probability P alpha alpha A times capacity if the SNR was gamma I. And gamma is alpha square capital gamma, alpha A square capital gamma. So alpha A and P alpha of alpha A values are given. Can substitute and find the ergodic capacity. What should be the SNR of a flat fading channel that have the same capacity as the ergodic capacity in the previous question? Then if you have flat fading, that means your alpha is just one. So your SNR is a constant value. Then the capacity is simply B times log of 1 plus gamma 0. And this they want it to be equal to ergodic capacity. We found ergodic capacity in question 16. You substitute the value, then solve this equation, you will get the value of gamma 0. So instead of the fading distribution given here, we had a flat uniform distribution. Then you would need a SNR of gamma 0 to get the same capacity. Then 18, what is the ergodic capacity if there is a 9% chance of outage in question 16? And in this case, this is equal to 1 minus P outage. So when there is outage, you get zero capacity. When there is no outage, you get the capacity without outage. So ergodic capacity is the average capacity with outage. Ergodic capacity was the average capacity for different when the fading was different. You could simply think of this as adding another, so modifying this distribution by adding another alpha value which is 0 with probability P outage. Then the remaining probability 1 minus P outage you divide in the same proportion among the alpha A's, something along those lines. But if you simplify that, that will turn out to be Simply 1 minus P outage times 1 minus P outage is the capacity, is the probability that there is no outage. So, in a sense, C outage is equal to 0 probability with this happens with probability P outage. C, let's call it good, is C ergodic that we calculated earlier. This happens with probability 1 minus P outage. Now the overall ergodic capacity is the average value of these two capacities. So it's 0 with probability P outage plus C ergodic with probability 1 minus P outage. And this term will go away. We are left with this. Okay, question 19, 20, and 21 are all just theoretical questions. You should find the answer in lecture 37 or 38 notes. Alright, with that I will end today's session. Good luck with your assignment this week.